we have slides. There we go. Awesome. Hi. Thank you very much for coming to our talk and for having us, for the organizers of the conference. So we are Diego Perez and Raluca Gaina. We are both lecturers in Games AI at Queen Mary University of London. And we are also founders and directors of Tabletop R&D, which is a spin-out from Queen Mary that offers automatic testing services for board game designers. So quite naturally, our work is focused a lot at the intersection of artificial intelligence and what these methods can do for tabletop games. By these games, we don't necessarily mean traditional board games like chess and Go, that probably a lot of you are familiar with. We are a lot more interested in more complex, modern board games that have a lot more moving parts to them and a lot of deeper strategic spaces where a lot of interesting interactions can happen between players. A lot of these games have many players, a lot more than two usually, which leads to interesting interactions between these players and the game as well. This here is Concordia, where you might notice that the yellow player right at the top is quite far ahead from the other two losing players at the bottom, the red and the blue there on the scoring track. And this type of scenario is quite interesting to demonstrate a potential interaction that might appear in such games where the losing players might consider forming a coalition against the other player to stop their dominance and work together in this otherwise competitive environment to give themselves more of a fair chance at winning the game. This here is Tapestry by Stonemaier Games. In this game, you have seemingly simple choices. So in your turn, what you do is you choose one of the 4 tracks to advance your civilization on. So you could be advancing on a military track and go invading neighboring territories. You could be inventing technology and furthering sort of your understanding of the world. You could be exploring more of the island and figure out what sort of resources and things are nearby. Or you could be advancing your science and your overall research and knowledge, right? So those 4 simple choices on the surface actually lead to very large branching scenarios and a lot of complex implications to gameplay. So this seemingly simple scenario is actually a very deep, complex game. It also has a lot of different cards, a lot of different tiles that the players can mess around with and interact with. And this leads to very deep strategic and rich spaces for making decisions, especially where we are talking about artificial intelligence players that would like interesting, complex environments to play with. And this type of game is also quite hard to balance, right? If I go back to that, there's so much going on in this game that actually from a balance point of view, it is quite hard to tune all of the features of the game, all of the different properties and cards and things going on to make sure that the players actually have an equally fair chance of winning the game, depending on their starting conditions and things that they can do along the way. So balance in this case is difficult to achieve, but balance also has a lot of different definitions, and it's quite a subjective context, right? We can have balance meaning that all the player choices available are sort of the same equal power, or we might want some player choices that are really dominant, but then there's a counter move that is available to sort of neutralize that and give more of a level playing field. But in some games, where you're just throwing burritos across the room, balance kind of flows out the window, together with the burrito perhaps, where here you're just looking at fun and chaos. And you want the players to be just enjoying the experience and not worry that much about how fair it is for somebody to be playing this type of game. So balance is very subjective, and ultimately it is up to the designer to define balance in the context of the player experience that they intend to have. There are a lot more interesting properties to these type of games, and I wanted to highlight a few more here. First is that they have quite a deep and rich cultural significance. They have a rich history, and they are spread all over the world. And it is very interesting to be able to track sort of how these games spread around the world, and how different regions in the world have played games, what type of games that they play, and how that propagates into our present culture and the games that we play and enjoy. These type of games also are very complex and have a lot of very interesting mechanics that interact with each other. There's just a lot going on in there and a lot to account for. We have games that have social layers. So board games are a lot about the experience that you have with other players that you sit down and play with, more so than video games, where they highlight the social dynamics also through house rules sometimes, where you decide, actually, we want to have a different type of experience at this particular time that we're playing. So we're going to be modifying slightly the way that we're playing the game. And some games also highlight particular types of social interactions a lot more than others, like resistance, that pits people against each other and asks some of them to lie to the others in the group. There are games with asymmetric roles, so giving each player a unique way of playing and interacting with the game. And we sort of try to bring all of these interesting properties from these games together in a digital space so that we can actually apply decades of AI research that we have been looking at over time. They've been studied a lot in video games, but we're really interested in seeing what we can do in this traditionally analog context instead. So some of the research that we've worked on is focused around this tabletop games framework, or TAG. This is open source and available on GitHub. And in here we have a large collection of games. So this is providing sort of a template to create games such that all the AI methods that we have available can be easily applied to a variety of games, such as we have their Descent, Journeys in the Dark, where we've studied sort of how different players are able to succeed in this game and what type of play styles they can exhibit. We have Pandemic, which is about controlling diseases spread around the world. And this is a cooperative game, so our agents are actually quite bad at winning. So there's some work to be done there at actually getting them to work together to solve the problems. And we also have environments like Terraforming Mars, which are very complex games that lead to a lot of complex decision-making processes. Within this context, we are looking at developing stronger algorithms that can deal with all of these different properties that I've gone over, such as multi-tree Monte Carlo tree search, which was created by James Goodman, and this is a recently published paper that you can check out. And the idea of this is to split off the decision-making process for each player and opponent, so that every time that you're thinking about what choices your opponents might make if you take particular actions in the game, you actually go to their own decision-making game tree and search within that. So you're kind of jumping between all of the different trees of different players. And this is a more scalable method for games with a lot of different players. But we're not necessarily only interested in agents that play games well. We're also a lot more interested in what these agents can tell us about the games themselves, so what kind of analysis we can use the players for. One type of analysis is for randomness. So a lot of games do feature randomness within them that plays a lot of different roles in games. It can be a crutch for players. It can give beginners more of a chance against skillful players. There are a lot of different aspects that randomness considers there. But actually, how much impact does randomness have in a particular game is an interesting question to consider, right? You don't want too much randomness. That would take away the control that players have over what they can do in the games. But you do want some randomness to be able to take advantage of the benefits that it does bring. This is an example here with Colt Express, where we can also disentangle the types of randomness that occurs in the game. So we can not only look at the probability of players winning depending on particular random setups, but also the types of randomness that appear in the game, how much impact each of those has on the potential game outcomes. And by disentangling this, we can allow designers to focus their changes on those aspects that maybe don't match their particular expectations, and they know exactly what in the game they might need to address in order to improve the player experience that they're aiming for. And also, we can look at profiling skill depth in games. So that is looking at the difference between players of different levels of skills. And not only as a static thing, so not only modeling different types of players and different levels of skill, but also how this difference might progress over time as players learn more about the environment and they become smarter, right? Does that difference sort of level off at some point? Does the gap narrow down a little bit more? Or is it always a big difference if somebody has played a game for a longer time than another player? Does it not matter how much sort of studying you do to be able to compete at similar levels to more proficient players? We are trying to answer this and many other questions in our research, and recently have taken it to the industry.
Okay, that's my part. So yeah, I'm going to talk a bit more about the tabletop games industry itself. So the industry is overlapping. It's independent, but it's also overlapping with the video games industry. So it's actually quite a big industry, not as big as the video game industry. It's about 13 billion pounds worth, and with expected growth of 14%. So you can see in this plot, this is showing how many games are being published every year, and there's an exponential growth in the number of games. So approximately about this time, there are about 7,000 games published every year, tabletop board games. So it's actually quite big. And it's been even bigger because of the digital platforms in which you can play these games. So maybe you know Board Game Arena or Tabletop Simulator, which are digital implementations of these games where you can play online with friends or with people that also use the platform, and you can play all these games over there. So it's becoming very popular. Now, on the question of how do board game designers make games, this is roughly the process that they follow, right? They have an initial idea or a concept, normally in a piece of paper with pens and post-its and very simple maybe cubes or dice that allow them to play with the rules of the game, modify it as much as they can until they are happy to create the design of a first prototype, which is something people can normally play with. It is better quality for the tokens, the cards, the different boards that you're using, and so on. And then at that point, they take those prototypes, take it to a table, maybe gather 4 or 5 people in a convention or in the particular events that happen around the year, and then put these people to play the game and give them feedback, right? And they try to do this not once, but as many times as possible, because every single iteration of this playtesting gives them information, data that is very useful for them to find out if the game is fun, if there are particular rules that are broken, and so on. Now, on playtesting itself, what they normally say is test early, widely, and often, meaning test as much as you can. Here's a few examples of people playtesting several games in development at Queen Mary, where we run this event early in February. But there are several problems with the way this is done at the moment, which are actually slowing down the way games are tested and created. One of them is that this is limited data collection. You can normally do in the process of a game, creating a game, about 10 rounds of playtesting, meaning changing the rules and test again. In one of these rounds, you might get 4, 5, maybe 10 groups of people playing the game. That's not a lot of data that you can gather. Also, that data is gathered manually, so all this process happening on an actual table where you have people playing the game, giving you feedback, you write it down in your notebook, and the data you get is as good as you are collecting this information. And finally, it's very subjective. Obviously, you have a specific amount of people playing this game, giving you feedback, and they might bring their biases into the process of testing, right? So what we thought is, what if we can just take a digital implementation of these games, have AI agents playing games, and analyze the games, giving information back to designers with games played at this speed. Actually faster than this speed, because we don't need the graphics. So that's what we do in Tabletop R&D. So as Raluca said, we're a spin-out of Queen Mary. We have already been working for about a year and a half, a bit more than that. We have already our first game designers that work with us, our first clients. And you can also see in this website what we're doing. But the main idea is that we allow these tabletop game designers to drastically reduce the time that they need for testing, in order to create better games by simulating thousands and thousands of games played with these AI players. Right? So what is the process that we follow? We take the game design, the idea of the game that's in development, and implement that digital twin in our tabletop games framework. We are essentially using a modular platform. That means that we don't really take a lot of time to implement these games. It's actually much faster than a video game because we have a lot of modular elements that we can share: cards, the actions on the cards, boards, counters, different type of mechanics that are common to many games. So we implement this first, and then we have our AI agents playing the games. Things like Monte Carlo research, that's sort of what we mostly do, because essentially that means that you can plug and play directly. Our agents can play any game that is just being created automatically, without the need of many games being played for training. And finally, what we do is we do a data analysis. We play all these games, we have a lot of data, and then we crunch that data to go back to the designers with specific information about what they are doing. So, a little bit of a differentiation here in this testing. So you might know tools like, for instance, this one by Model AI, that essentially what it does is testing the implementation of a game where you have a bot moving around, jumping, colliding versus walls and so on, try to find elements that are broken in the implementation. What we do in Tabletop R&D is testing the design of the game. We give information to the designer about issues that might be with the rules and the mechanics that are implemented in the game. So, I'm going to show you a few examples of what it's possible to do and what we've been doing so far. So one of them is this work by Alan Wallat. It's a game that is in development now called Serious Smugglers, in which you play as some contrabandists that are smuggling in the universe, going to different planets, getting resources, trading, stealing, and so on. So the first thing we did is we just run our agents. We realized that poor agents normally try to take points early in the game, while advanced agents are clever in the sense of they are able to understand the mechanics better and find out points that are given at the end of the game. We analyzed first for 2, 3-player, 4-player version of the game, so in different game termination conditions. So there are 3 of them. Those they're showing that 2 of them were happening often and the other one not happening at all. Interestingly, one of the things that Alan told us is that this is corroborating with the player the human playtesting, because this is not meant to be substituting human playtesting. It's meant to be a corroboration or refutation of the data that they also acquire with humans. So that was correlating with what they were observing. Alan made a few changes in the games, and then the few changes that were affecting parts of the rules of the game actually made that only one of these termination conditions, and that one over there, these 2 in the middle that were now in the game, they weren't triggering at all. So we can do iterations over the design and explaining how these changes in the design are changing the mechanics of the game, overall game. We also work with Puerto Rico. This is a kind of an old game. It's 2001, so we did not work with the designer here, but we implemented it in our system in order to analyze a little bit more of what can we do. Another very valid metric that we can provide is essentially opening moves, right? So we show that the builder, which is one of the opening moves that you can take, is the best option for the first player. While, for instance, for the second player, the mayor tends to be the stronger move. So that basically tells you which are good opening moves for the game, and that might be something that the designer wants or doesn't want. We also find a very interesting fact in which if you have a newbie player playing against Puerto Rico with you, put it to your left, because that means that you have more chances of winning. So little tricks that exist there, and the designers might actually want this or not again, and we are there to inform the designers about these particular things. Another example as well, Big Fish by Charlie Bean. This is a car game, also in development. We saw that it has first player advantage, a very slim first player advantage. About 52% of the games were won by the first player. There's nothing really wrong with this. Really, chess has a first player advantage, but again, depends on what the designer wants to do. Another interesting thing that we check is number of times the leading player changes. So if you are losing the game, how often happens that you're actually able to change and become the one that is winning at that time as well. Interestingly, Charlie also told us that for this particular case, especially for the cases where you have 4 players or 5 player games, the data that we're providing here was much more useful for them because, again, data collection for large number of players is quite complicated and quite time consuming. So, again, providing data that is difficult to obtain for them. Finally, for tourists, which is a very complex worker placement game, we are showing things as well like the cars that can be used, the strength of these cars. So you can find out overpower and underpower places to put your workers, or cars that exist in the game, or locations where you can do certain things. So again, we provide all this information, and at the moment, this game they're working on the 2nd edition now, and we provide the information. They're going to be working on some modifications, and we'll see because they want to address some of these imbalances, and they're going to see if they can make some changes so the imbalances go away. And finally, the last thing I'm going to show is that what we do, because we implement the digital twin, we also parameterize the game. In this case, what it means is that we extract the parameter values that are of interest that can be easily changed. So for instance, for the car game I was showing before, the default game is played with 20 cards per deck. But you can change this, right? You can decide to modify it and then see how the game experience changes. So we actually provide this tool to the designer where they can, on a browser, play the game. They can modify the different elements. So for instance, here we put 30 cards rather than 20 cards. That means playing with 120 cards, I believe. And then changing also the points that you get for different actions. And then essentially the designers can play versus humans or versus different AI players, very simple players, or strong players like MCTS agents. And then when they play the game, they can themselves see how the game develops. So they can experience the game firsthand. In this particular example, we don't show here some statistics, but we have a newer version of this in which you can actually show as well the metrics that we are also calculating across several games. So this is what we do. I hope you found it interesting. Raluca and myself are happy to talk to you, answer questions, or whatever you need. Thanks.